Good morning everyone. Welcome to the video lecture of the digital electronics, and the topic which we are going to study is the analysis of synchronous sequential circuits. So till now I believe that you have covered the sequential part. You know how the flip-flops work, how we can design the flip-flops, how we can convert one flip-flop into another type. In today's lecture we are going to study the analysis of sequential circuits, that how any sequential circuit can be used to draw the state tables, or to how basically the sequential circuits can be designed, right? So the analysis of sequential circuit, in this we are going to study the behavior of the sequential circuits which determined from the inputs, outputs and the states of its flip-flops, right? So in this upcoming lectures, we are going to use the term states again and again. Now, what basically means the state is, for example, we have one complete digital circuits. The inputs will be applied with the help of some combinational network, and we can also collect the outputs with the help of some combinational network. So it will have some inputs, some outputs, and between that there will be n number of flip-flops which will be used to store the data. So if you take the output collectively from that flip-flops, it will be named as some state, right? So both the output and the next state, and the next state are the function of the inputs and the present state, right? We have also seen in the flip-flops, when we analyze the flip-flop, the next state output is the function of your previous output as well as the input, right? So analysis is the reverse of synthesis of design. It is a process to understand the function of a circuit, and there are two modes of synchronous sequential circuits. With the help of these two modes, we can analyze any sequential circuits. So these two modes can be classified as Mealy circuits and Moore circuits. In case of Mealy circuit, we are going to have some combinational logic. Some state registers will be there. This state register will be the combination of, it will be the combination of flip-flops, right? And your outputs will be collected with the help of some combinational logic. So this type of circuit where your output function is the function of your inputs. It is the function of inputs and some states. From here we are going to have some states, right? So when your output is the function of some inputs and as well as the states, it is the machine is known as Mealy type machine. Whereas in case of Moore type machine, your output is the function of only states, right? So in this case of Moore machine, your output function is only the function of your state variables. Okay. So let me once again explain that what basically a state is. Suppose we have one circuit, and it contains a few flip-flops. Okay, some clock will be applied, right? It will have some outputs QA, QB and QC. Their inputs are applied with the help of some gate logic, right? With the help of some gate logic here, their inputs are applied. Okay. So when these outputs are collectively read, this is known as one state. Okay, so whenever your next clock pulse is applied, this state will be changed and your final output will be changed. Similarly, we can collect the outputs in any way, right? So the basic difference between Mealy and Murray is in case of output function, the output function is dependent on the input as well as the states, and whereas in case of Murray machine, the output function is the function of only states. So another difference in case of Murray machine, the output changes only at the triggering of the clock edge, whereas in case of Mealy machine, the output changes as soon as any of the input changes, and however the states cannot change until the triggering of the clock edge. Conceptually, they are simpler and usually require more states, whereas in case of Mealy machine, they require a fewer states as compared to your Murray machines. Murray FSM, as the outputs can have the different values in a single stage. Since it has more circuit delay, more logic is needed to reduce the decoder to decode the output end, and therefore they are a bit slow. They react fast to the inputs. In case of Mealy circuit, they behave fast because they are directly dependent on the inputs. So if you represent graphically, if you draw the state diagrams, in case of Mealy, we have these states, and on these transition arcs, these are known as transition arcs. Okay, so your input and output variables are defined on the transition arc itself. These are known as your states, and in case of Murray machine, your states and the output is defined inside the state circle, and here we are going to define the inputs on the transition arcs. On the transition arc, we are only going to define the inputs. So this is some simple state diagrams of your flip-flops. Let us try. Let me explain this JK flip-flop, how the state diagram of JK flip-flop is designed. So to draw the JK flip-flop, first we write the characteristics table. Characteristics table of the required flip-flop. So here I am going to explain the state table of JK flip-flop. We know that we have the inputs JK and the previous output QN, right? And the next state output is QN plus 1, right? So with the help of 3 variables, we are going to have 8 combinations. One 0 0, 1 0 1, 1 1 0, and 1 1 1, right? So in case of JK flip-flop, we know that, so we have these 4 values of JK, 0 0 0 1 1 0 and 1 1, possible output combinations 0 1 in each case. So the first case, when the value of J and K is 0 0, we have the no change, so the output will remain same. So when the value of K is 1, output is 0. When the value of J is 1, output is 1. And when the value of JK is 1 1, we have the toggle values, right? We have the toggle values. So in this we can see that there are 2 types of states, state 0 and state 1. Okay. So we name them as 0, we name them A state, and 1 we name it as B state. So A state, we are going to collect the outputs 0, and B state, we are going to collect the outputs 1, right? And we know that in case of Murray representation, your inputs are going to represent on the transition arcs. So first case, when the inputs are 0 0, it will remain in 0 state, right? So the previous state is 0, it will remain in 0 state. So the value of jk is 0 0. This is jk is equal to 0 0, right? So it will remain in 0 state. So when the value is 0 0, the previous state is 1, it will remain in state 1. Fine. So next case 0 1, it will remain in 0 state. It will remain in 0 state. So the next possible value here, it will be 0 1. For the next case, for 0 1, it will we have the transition from 1 to 0. From 1 to 0, it is in 1 state and it will be transitioned into 0 state when the value of jk is 0 1 and it is in 1 state, it will be transitioned to 0 state. Next 1 0, the inputs are 1 0 and we are in 0 state, it is transitioned to state 1. 1 0. Next 1 0, we are in 1 state, state 1, and we are going to remain in 1 state. So here the next possible value is 1 0. From 1 1, from 0 state to 1 state, from 0 state to 1 state, here the next possible value is 1 1, and in the last case from 1 1, we are going to here the output should be 0, it is toggled from 1 to 0. So here the next possible value is 1 1. So because in this state diagram I have represented the inputs on the transition arc and outputs with the state. So it is a Murray representation. It is the Murray representation of JK flip-flop, right? So this way we can design and analyze any flip-flop with the help of state diagram. So next is how we can analyze any complex sequential circuits, sequential circuits which are synchronous in nature. So first step is, there are few following steps which we are going to follow. The first step is draw the circuit diagram. Find the inputs being applied to the flip-flop. If there are n number of flip-flops, what are the inputs to each flip-flop, right? So second step is find out the inputs to each flip-flop. Then write the next state output of the flip-flop. Next state output, if you are using the D flip-flop, whenever the clock pulse is applied, whatever input is applied, it will be your output, right? So the next state output will be applied directly proportional to the applied input, right? But in case of if you are using T flip-flop or JK flip-flop to analyze any circuit, the characteristics equation is used. We are going to use the characteristics equation to find the next state output. The first step will be write the state table, which includes present state and next state, and finally we will draw the state diagram and we will conclude the operation. So let us take this example. This is one example where we have the three flip-flops, flip-flop A, B and C, right? For example, a positive clock pulse is applied to the flip-flop and we can also use clear signals in the flip-flops also. In this diagram I'm not going to use that. So in this connection, so first step is draw the circuit diagram. So we have made the circuit diagram. This is your step 1. Second step is we have to find out the inputs of each flip-flop, right? So let this input is named as DA, DB and DC. Okay, so step 2, inputs to each flip-flop. Inputs to each flip-flop. So DA, we can see that DA is connected to the QC bar. DA is equal to QC bar. Then DB, it is equal to QA, and here DC is equal to QB, right? Step 3, we have to find out the outputs, right? So find the outputs. In case of D flip-flop, whatever the input is applied here, the output will be same, right? So suppose your initial outputs are 0 0 0. So the next state output we can represent it as QA plus, QB plus and QC plus, which will be directly equal to your DA, DB and DC, whatever the values we are going to apply, right? So the step 4, we have to draw the state table. We have to draw the state table. So in the state table, we have the present state, and next state, right? Present state and next state. Suppose your present state is represented by QA, it is indicated as QB and QC, and your next states are QA plus, QB plus and QC plus. So suppose your outputs are initialized to 0 0 0, right? So 0 0 0, initial outputs are 0 0 and 0. So here Q bar, QC bar will be 1. Now we can see that this 1 is connected to the DA input, right? So its next state will be 1 0 0, right? Next state will be 1 0 0. Whenever your clock pulse is applied, this one will be appeared at this output node, right? Again here your value is 1. So let me complete this table first. 0 0 0 0 0, 1 0 1 0, 0 1 1, 1 0 0, 1 1 1. Okay. So now from 1 0 0 state, it is now at this state. From 1 0 0, we are again going to have 1 1 0. Now we have come to this stage 1 1 0. From here I will have 1 1 1, right? From 1 1 1, because now we have 1 1 and 1. Let me change this pen. Now I have here the state 1 1 1. Here QC bar will be 0. So 0 will be connected to DA. So now I'm going to have 0 1 1. Now I have reached to this stage 0 1 1. Now, right? So now I am having 0 0 1. Now I have reached to this stage 0 0 1. Now I'll have 0 0 0, right? And this stage, if I have this value 0 1 0, if I have this value 0 1 0 0 1 0, here I am going to have 1. This one will be fit back here. So I am going to have just a minute 0 1 0 1 and 1 1 0. So here I am going to have 1 1 0, and we have left one state, I think 1 0 1, this 1 0 1 state. If I have 1 0 1 state, here your QC bar will be 0 and this will be fit back here. So we are going to have 0 1 0. So here I am going to have 0 1 0. Here I am going to have 1 0 1 state, 1 0 1 state. Okay. So this way we are going to complete the table, present state and next state table. So in this table we can see that let us draw the state diagram for this. So the states are named as, from 0 0 0 it will go to 1 0 0 state, right? From 0 0 0 it will go to 1 0 0 state, right? From 1 0 0 it will go to 1 1 0 state, 1 1 0. Then from 1 1 0 it will go to 1 1 1 state. From 1 1 1 it will go to 0 1 1, 0 1 1 state. Then from 0 1 1 it will go to 0 0 1, 0 0 1. From 0 0 1 it will again go back to 0 0 0 state, right? And two states which we have written in blue, from 0 1 0 it will go to 1 0 1 state, and from 1 0 1 it will go to 0 1 0 state, right? So two states are isolated. From 0 1 0 it will go to 1 0 1 state, and from 1 0 1 state it will again go back to 0 1 0 state. So lastly we have to conclude this circuit, that what kind of circuit is this, what kind of behavior is this. So we can conclude that in this circuit, two sequences are isolated from the main sequence and the rest of the sequence behave as a twisted ring counter, Johnson ring counter. So where your values of 1 is increasing gradually and then decreasing back to 0, right? So this way we can analyze any sequential circuit. So let us quickly take another example. So we have this example. In this example, your inputs are applied via some combinational network, right? Your D inputs are applied via some combinational network, and Y output is dependent on this X. So this is the Y output. This is the only Y output which we have again drawn here. So if you check this network, the value of DA, the first step is we have to draw the circuit, right? Let us quickly do this. This is the step 1. The step 2, we have to find out the inputs. So here your inputs are, this is my A signal, right? Here we have the X signal, and here we have the B signal, okay? And from this gate we are having the A bar and X, and here I am having the A signal, and this is the A signal, and this is the B signal. This is the B signal, A signal, and here we have the X and X bar. So now we can see that the value of DA is AX plus BX. The value of DB is A bar X, and the value of Y is X bar A plus B, right? So these are the values of the inputs. Inputs of each flip-flop, right? So step 2, we have to find out the outputs. We are using D flip-flop. So same inputs will be reflected back to the output. So DA plus, A plus, here your output is defined by A. So next state output, I am going to define it by A plus. It will be your again AX plus BX. B plus will be A bar X, and finally we are going to have some Y, right? So the next step is we have to find out the present state, draw the present state, next state table. So quickly draw that, complete the table. We have the present state, next state. In the present state, I am going to have the values your A, B and X. We have the A plus, B plus and Y, right? So okay, we have the DA, zero 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 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 and 1 1 1, right? A plus, the value of A plus is AX plus BX. The value of A plus is AX plus BX. B plus is, the value of B plus is A bar X, and Y is my X bar A plus B, right? So we can also write it as A plus B X, right? So wherever you have the value of X is 0, the product will be 0. So I am going to write directly 0 0 0 and 0. And where the value of A plus B is 0, we are having A plus B is 0 at this point. At this point, here I am going to have 1 1 and 1, right? Next, B plus is A bar X. So the value of X where is 0, this product will be 0. So 0 0 0 and 0. Next, A bar, wherever the value of A is 1, A bar will be 0, the product will be 0. On the rest places, we are going to have values 1. Next, y function is A bar, x bar, A plus B. X bar means whatever, wherever the value of x is 1, here I am going to have values 0, and then A plus B, wherever it is 0, so 0. On rest places we are going to have 1. Okay, on rest places we are going to have values 1. So state table is completed. Next we have to draw the state diagram. Okay, from state diagram we can see that we can also name these states as A, B, C, D, E, F, G and H. So here from 0, 0, 0 it will go to 0, 0, 0 state. From 0, 0, 1 it will go to 0, 1, 0 state, 0, 1, 0 state, C state. So this way we can also draw the state diagram. So here I am going to draw because your inputs, your output is dependent on the input. So it is the Mealy diagram. So in case of Mealy diagram, your inputs and outputs are marked on a transition state. So I am going to mark it on a transition state. So we have these 4 states. We have these 4 states 0, 0, 0, 1, 1, 0 and 1, 1, right? So we have the 4 states 0, 0, 0, 1, 1, 0 and 1, 1 state. 4 states are there. From 0, 0, when the value of x is 0, the value of y is 0, it will remain in same state. These are the values of x slash y, x and y. From 0, 0, it will go to 0, 1 state. It will go to 0, 1 state when the value of x is 1 and y is 0. From 0, 0, it will go to 0, 1 state, right? Okay. Then from 0, 1, it will again go back to 0, 0. The values are 0, 1. From 0, 1, it will go to 1, 1 state. The values are 1, 0. From 1, 0, it will go to 0 state and the values are 0, 1. From 1, 0, it will remain in same state when the values of x is 1 and y is 0. From 1, 1, it will go to this state. The value of x and y is 0, 1 and it will go to this state when the value of x is 1 and y is 0. So this way we can analyze this circuit where your inputs are applied via some combinational network and output is collected via some combinational decoder, and we have this memory part where you have the n number of states, right? So this way we have to find out that what kind of circuit is there, whether it is Mealy or Moore. Accordingly we have to draw the state diagram. So thank you so much for today's lecture. Thank you.